Alright, it's been a while, but in previous lessons we covered a few things with respect to circular motion. Let's just look at them really quickly because they are still related to what we want to do today. The time it takes for an object to go around from its starting point all the way back, that is called the period. And we said that that is measured in seconds. Its symbol is a capital T. We also introduced the concept of frequency. How many times does it occur per second? So if your period is in seconds, frequency is equal to 1 over T. The next thing we did was a demo which showed you that at any given time, if things deviate from their circular path, they come off tangent to the circular path, and essentially that's our velocity. Velocity, we said, was a distance over time. So what we do is we go, well, this distance is the circumference of the circle, that distance is 2 pi r, and then the time it takes to do that is the period t. So you get your velocity, and remember we called it tangential velocity, which always tells us that the direction is tangent to the circular path. So it's a pretty easy thing to calculate. When we're looking at objects, what we have to do is we have to see what they're doing. They're always changing direction in this. They're moving at a constant speed, or at least we're restricting ourselves to something that's moving at a constant speed in a circular path. So let's say hypothetically, I've got a mass here. It's, we'll say it's 3 kilograms, which is a lot, and it's moving in some sort of circular path. And we'll say that the radius of that path is 0.25 meters, 25 centimeters essentially. And let's say that the time it takes to do that is, say, 0.75 seconds. So this is pretty easy to calculate all of the things that we just reviewed here. The period's 0.75 seconds. If we want the frequency would be 1 over 0.75. Remember, that is units of inverse seconds, which is what we call a hertz. And that is abbreviated with a capital H, lowercase z. So that would end up being 1.33 hertz. If we want the velocity, pretty easy to do, it would be 2 pi r is 0.25. And then we're going to divide it by the period of 0.75. So you got 2 pi times 0.25 divided by 0.75. And we get 2.09 seconds, or meters per second, sorry. And they're all pretty easy to calculate. Now, if we looked at any given point in time, if I said, for example, well, where's the direction of the velocity there? You can just draw your tangent line and say, well, it's that way. Now, here's the thing. The speed is not changing, but the direction is. And this is where we're going to get into the concept of centripetal acceleration. Velocity has both magnitude and direction, and what's changing is direction is changing. The size of the velocity is not changing, but the direction is changing. And if the direction is changing, that means that the velocity is changing here. So we have something called centripetal acceleration, and if we're looking for the direction of that vector at any given point in time, it's always towards the center. So if I looked, let's say, over here and said, well, where's this object going in terms of its velocity at that point in time? It's still tangent, but it's that way. And the acceleration you're going to find is always pointed towards the center. So you have an acceleration vector that's pointed towards the center. And this is what we call centripetal acceleration. What this does is it redirects the velocity. It doesn't make it grow. It redirects the velocity. It doesn't make it grow. It doesn't make it shrink. It just changes its direction. So if you want to calculate it, it's a very easy calculation. It's A. I usually use a subscript of C to denote that we're dealing with centripetal acceleration here. It's v squared over r. So we have the ability to easily calculate it using our numbers that were given in the initial set of problems here, because we have v now. It's 2.09, So A would be equal to 2.09. You'd square it. Let's actually look at the units. Put it in meters per second here. We'll square it. And we'll divide by 0.25, which is our R value. So you got 2.09 squared divided by 0.25. And that's meters here. And if you look here, you get 17.472. And when you square this unit, it would be meters squared per second squared. But then you're dividing by meters, so one of those meters cancels out, and you just get meters per second squared. That's your centripetal acceleration, and it's not a rate of growth. It only describes how the direction is changing. So the last thing we want to take a look at is the second law. When you're looking here, if we have something that's rotating, we know that our object is moving that way. We know that it's accelerating towards the center. Newton's second law stated that, well, if you have acceleration, if you recall it, it was F net equals ma. We said that the net force has to cause it. So you have to have some sort of force causing that. So there also must be a net force pointed towards the center as well. And those are the direction of your vectors. You got two always pointed towards the center, one always pointed tangent. And we can also write Newton's second law a different way. Since A equals V squared over R, we can also write it says mv squared over R if we want to. So using the numbers that we had here, 3 kilograms and a velocity of 2 and an R of 0.25, let's just calculate the net force here real quick. It would have been 3 times 2.09 squared all over 0.25. And what I'm getting is that in order for this circular motion to occur, there had to be a 52 Newton force behind it. So if you think about it, if you're swinging something over your head, you can physically feel that tension in the string when you're doing it. And that is what this is, this net force here. So you can actually use this or this. It's up to you. You'll get the same answer either way. So if we took our value of A here and put it into there, we would still get the same 52 newtons, 52.4 newtons if I want to be a little bit more exact. So I think that should be enough to kind of give you guys enough guidance to get started on that worksheet that I gave you on Friday. I'd say it's probably going to take us at least 2 days to get through it, so we'll make it our goal to start it today and see how we do on that sheet.